So tonight we're going to be talking about Lewis structures and the different theories that shape the bonding of molecules. So there are three main bonding theories that we learn in general chemistry. VSEPR theory, which says that electron-dense groups will repel each other as far as possible, and that will dictate the general shape of the molecule. Valence bond theory helps us explain why, for a molecule such as methane, which has in the carbon, the central carbon has two s orbital electrons and two p electrons. Those should have different bond lengths, but methane has 4 bonds to hydrogen, exactly the same length. Well, valence bond theory and the idea of hybridization explains why all these bonds from the central atom have the same length and strength. And then, of course, we know molecular orbital theory, which is the idea that two individual valence orbitals will mix and create a molecular orbital with delocalized electrons over the entire molecule. And I think that the most important thing that I want to drive home before your midterm on this is that while all three of these theories are the same, or they all are correct, they're all different and explain different things that we observe. They're all parts of the same puzzle. So we don't say, oh, it's VSEPR theory or valence bond theory or molecular orbital theory, which is right. We say that all of these different theories give us a better idea of the nature of molecules and what gives them their shape. Well, good thing, we're not going to be talking about molecular orbital theory tonight, but your instructors all are experts in this. And so if you do have questions about molecular orbital theory before the test, and specifically things like which ones, when do you see mixing of these orbitals versus not mixing and things like that. So bring those questions and make sure you get that cleared up. But tonight for the lab, we're just going to be focusing on VSEPR theory and valence bond theory and answering some questions. So I'm going to first show you what the lab looks like. So give you everybody a sense, if you haven't already dove into it, before we talk about the topics. That way, if you have a question, once you've seen it, as the topics come up, you can ask. I don't want to give this to you at the end and then you'd be like, oh wait, now I have a bunch of questions. So you go into assignments as usual. Hopefully we know what we're doing now. This is our last lab. All the way at the bottom, of course, because it's our last lab, experiment 13, Lewis structures, molecular shapes, hybridization, and bonding. So, of course, yours won't say preview, it'll say start the quiz. Take a note that there's no time limit, multiple attempts. You're going to keep the highest score. The idea here is getting the mastery of this material. That is what we want from all of the students. So try to see this as an excellent opportunity to get this help before you take the test. If you do the lab after the midterm, you still have to take the final. If it's not even heavily covered on the final, this is going to be huge in the next course in chemistry 156. And so you're going to want to make sure that you have a good understanding of what gives molecules shape. So this is really useful for everybody. Okay, so there's going to be two main parts to this lab. The first part is going to be simply talking about this SO4 2-, this sulfate ion. First, you're going to draw it, and you want to be able to draw the resonance structures of it. And we'll come back to that in a little bit, and I'll give you a little bit of help there. You're going to answer a bunch of questions on this one structure. So you'll have to be able to draw the Lewis structure of this ion, and then all of its resonance structures. And then the next thing you're going to do, so it gives you specific instructions on how to set up your paper. So this first part, you just split one piece of paper in half, and you top and bottom as shown. And then the rest of the lab, 5 more pages, you divide into quadrants and you put one structure into each quadrant. There are 20 structures as listed here. So takeaway, 21 structures that you have to draw tonight. 21 Lewis structures, resonance for some of them. That's it. So if you think that you can't draw 21 Lewis structures in 3 hours, then this is the place you should be for practice. Now the question is, once we draw the Lewis structures, can we analyze them and get all the data out? And that's where, if you can't do that, you're going to get really bogged down really quick. But note that this is where we're going to begin with drawing our Lewis structures. And a large chunk, 30% or something of tonight's grade, will be uploading these Lewis structures. So make sure that you get all of these and you get them correctly. And so just giving you a sense of what kind of things that we're going to be asking of you tonight. So there's going to be 2 parts in the quiz. So part 1 is shown here. And again, we're talking about the sulfate ion. There's going to be questions, actually, I think 15 questions about bond order and and breaking down all of the sulfate ion and different aspects of it. And so as you can see, question 15 here, and this is the end of part 1. So 14 questions on those resonance structures. And again, right after this, we're going to get into all the different aspects, all the different things that you're going to be asked to be able to recite tonight about these molecules. So after part 1, then we do those 20 different structures. So the first one, CF3Br, you can see here, and then there's just a bunch of questions: electron domains, bonding domains, non-bonding domains, lone pairs, hybridization. I keep going, 7, 8, 9, 10. How many of this? Bond angles, sigma bonds, pi bonds, atomic orbitals. So all of this information about a single Lewis structure. So if you can draw the Lewis structures, no sweat, you're in good shape. And if you understand these concepts, and again, we'll go through the checklist together, then you're going to be in good shape. But if you don't know what bonding domains are, if you don't know how to identify hybridization, if you don't know how to identify molecular shape, then each single one of these questions will be really, really time consuming. And so then be prepared for this lab to take you a little bit longer. But you do have an unlimited time supply, so just keep that in mind. 35 questions here. And this last question, 35, is worth 6 of the 16 points. And it's simply uploading the PDFs of your Lewis structures. So you'll start with your Lewis structures, but then 34 questions are going to involve breaking those Lewis structures down and understanding the VSEPR theory and the valence bond theory, and understanding exactly what gives that molecule shape. So without any more of that, let's dig into what it's going to look like. So the core of tonight will be being able to draw Lewis structures. And then, so we'll practice a few Lewis structures. And I know almost all of you are experts at this point, but let me just walk through it so that we all have the same kind of process. And that way, if somebody is missing something, sometimes there's just a little detail in the process that gets lost, and you need to just put that little detail into place, and then you feel really confident. So we're going to look at NF3, and we're going to build a Lewis structure for it. But first, I'm going to tell you the 5 steps of building a Lewis structure. So the first step is we're going to build a skeletal structure of the atoms relative to each other. We're going to choose the central atom as the atom that comes from the smallest group. That means it has the lowest number of valence electrons, and thus it will make the most bonds. It needs the most electrons to fill its octet. And so then we're going to count the number of valence electrons before we do anything else, before we make any bonds or any lone pairs. If it's a polyatomic ion, either a negative anion or a cation. For an anion, you're going to add electrons for every negative charge. For a cation, you're going to subtract electrons for every positive charge. Then you're going to draw single bonds to every single one of the surrounding atoms from the central atom and count 2 electrons for each bond. Then you're going to distribute the rest of the electrons as lone pairs around the outside atoms so that each ends up with an octet, a total of 8 electrons, with each covalent bond counting as 2 electrons. And then if the central atom doesn't end up with an octet, then you're going to start moving lone pairs into double bonds until you fulfill your octet. So let's try it for NF4 really quick. So first we'll draw our skeletal structure. So we'll put nitrogen in the center because it is in group 15 or 5A, and fluorine, of course, is as a halogen in group 17. And so we'll put it in the center. It needs to bond more. We'll surround it with fluorines. Then we'll add up our valence electrons. So nitrogen has 5 and fluorine has 7 times 3 of them. There's no positive or negative charge. So we get 26 valence electrons. And so the next thing that we're going to do is form our bonds, and we'll start counting the 26. So 2, 4, 6. Now we'll start adding our valence electrons to make octets. So 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We need 2 more, and we don't have an octet on our center atom, and so we put 2 there. And so this would be the structure of our NF3, and we'll talk more about all of the different details in a little bit. Let's, really quick pro tip in case you don't already have this down, and I'm sure you do. Hydrogen always forms 1 bond. Carbon normally forms 4 bonds. It can form a double bond and 2 single bonds, but you're normally going to see 4 bonds there. Nitrogen normally forms 3, oxygen normally forms 2, halogens normally form 1. So you can kind of start to take some of those ideas, and it will really help you understand what bonds you should expect, right? Our nitrogen here, how many bonds did it form? 3, and it has a lone pair. So it works. Let's try one more, and then we'll get into some more of the details. So again, we're going to start with our skeletal structure. Phosphorus is in group 15 again, and of course chlorine is 17, so we'll put phosphorus in the center, surround it with chlorine. So phosphorus has 5 electrons plus 7 for chlorine times 2, and that, minus, so there's a minus charge here, so I made a mistake. Nothing like a mistake on the last night. So a negative charge, which means 1 more electron, so we'll add 1. And so that gets us to 20 valence electrons. So now we have our skeletal structure, so we can go 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. Now we've fulfilled our octets, and the last thing that we do is we place brackets on ions of Lewis structures. We put the charge on the outside. It's negative charge. Okay, so make sure that we all are really familiar with the idea of resonance. So sometimes you can draw a molecule. Here we have our benzene ring. Here we have ozone, which is a very common description. This will be something that you'll see tonight in the lab. Ozone has 1 double bond and 1 single bond, but you can draw it in 2 structures, with the single bond over here or the single bond on this side between A and B or between B and C. And so what we find with resonance structures is that instead of having a double bond and a single bond, the double bond electrons delocalize between both bonding areas, or in this case, the 3 double bonds delocalize between the 6 bonding areas. And so they're kind of shared in between. The takeaway is that in the lab, we can measure the distance of these bonds and also measure the strength and the bond order. Those all mean the same thing. And what we find is in resonance structure, they are the same length, the same bond order, the same bond strength. And that means that they're both not single bonds or double bonds, but somewhere in between. And that's the idea of resonance structure, is sometimes you can draw multiple ways of drawing a molecule with single and double bonds. I'm changing locations. And what we found out is that they are somehow a superposition of all of those double bonds and single bonds. So the result is that when we find a bond order, remember a bond order of a single bond is 1, a bond order of a double bond is 2, a bond order of triple bond, guess what, is 3. So we say there can't be fractional bond orders, but yes, there can be because of resonance. And with resonance, the bond order becomes how many pairs of electrons are shared. So we have 1, 2, 3 pairs between 2 groups of space. So 3 shared pairs of electrons over 2 bonding atom pairs. And that gets us to a bonding order of 1.5. So in between 1 or 2, and that's backed up with the data. When we measure the length of this oxygen O2 bond, we find that it's in between the measured lengths of an O2 single bond, O2 double bond. It has a 1.5 bond order. Another thing that's really important to make sure that we have down is the concept of formal charge. So the formal charge, once we draw any resonance structure, any Lewis structure for that matter, we can count the environment of each atom's electron density. So the idea of the formal charge would be how many electrons are on the atom if all the electrons were shared equally, and how does that relate to the number of electrons that atom expects? So for instance, with oxygen, we normally have 6 valence electrons. That's what an oxygen atom expects. So the question is, what is the environment of this oxygen atom when we can calculate that by taking the number of valence electrons we expect and then subtract the number of unshared electrons plus the number of half of the number of shared valence electrons. And all of that means is you count every lone pair individually, or not lone pair, 2 electrons, every electron, and then you count 1 electron per bond because 2 electrons are here and 2 electrons are here. So what that means is that for this resonance structure, for atom A, it should have 6 electrons, and it has 1, 2, 3, 4, 5, 6. So 6 minus 4 minus 1/2 times 4, which is 2. So 6 minus 6 is 0. So that means that it has the environment that it expects. It has a formal charge of 0. Here now we have 1, 2, 3, 4, and 5 electrons on B, which gives it a +1 formal charge. And here we have 1, 2, 3, 4, 5, 6, and 7 electrons on C, which gives it a -1 charge. And of course, with our resonance structure, we can shift the double bond over here, which makes our -1 charge on A, our +1 charge stays on B, and now our 0 formal charge is on C. So make sure that you're able to draw formal charges. What do we do with formal charges? Well, we can make sure that we choose the most correct resonance structure. And this gets a little bit tricky because I just said, hey, these are superpositions of each other. So do they all exist or none of them exist? Well, the truth is that the electrons are going to sit in the molecule where they are most comfortable. And we can kind of predict that a little bit using formal charges. So the trick is that when we're making resonance structures that can have a bunch of different formal charges, we want to do 3 things. 1, we want to make sure that we have the smallest number of formal charges as possible. So minimize formal charges. The second thing we want to do is we want to make sure that we don't have the same non-zero formal charge on adjacent atoms. Atoms are not going to want to sit next to each other and have an uneven distribution of electrons without trying to redistribute electrons or just break the bonds that they're forming. So they will settle into the lowest energetic state. All nature does that. And then finally, the more negative formal charge will reside on the most electronegative atom or the smallest atom, right? So those things Linus Pauling taught us are intrinsically linked. And so we see the math here for these formal charges for nitrogen, carbon, and oxygen for structures 1, 2, and 3, as shown here. And so without going through all the math, you can see, right, that nitrogen wants 5, it has 7, and so it has a -2 formal charge. Carbon wants 4 normally electrons, and it has 1, 2, 3, 4, so it has a formal charge of 0. Oxygen has a +1 formal charge, so you have a -2 and a +1 formal charge over here. So that's more than we would want. So the second structure, now we have 1, 2, 3, 4, 5, 6 on nitrogen. And so that's a -1 charge, but now we have 6 on oxygen, so a 0 formal charge, and 4 on carbon, so a 0 formal charge. So that's better than structure 1. But the problem is this last thing, we want the negative charge on the most electronegative atom. So nitrogen is slightly bigger than oxygen, which means that oxygen is a little bit more electronegative. It's closer to the carbon, and so it has more electron density on it, which means that we want structure 3, which has 1, 2, 3, 4, 5 on nitrogen, 1, 2, 3, 4 on carbon, so 0, 0 formal charge. And then 1, 2, 3, 4, 5, 6, 7 on oxygen, which it normally wants 6, so it has a -1 formal charge. This giving it the smallest number of formal charges and putting the formal charge onto the most electronegative atom. So this makes it the most correct resonance structure. Okay, so let's just really quickly go through this one more time on drawing resonance structures. And this, of course, is that sulfate ion. So I'm not going to show you all of the resonance structures. So if you're like, oh, I'm just going to watch this video later and then I'll be done with the lab, I'm not going to do it that easily. But I will help you out. We're reaching the end of the term, and I think that we need less mysteries and more answers. So let's try it out. We have sulfur and 4 oxygens. We'll draw our skeletal structure. Sulfur is going to be in the center, and oxygens will surround it. And so we're going to count our valence electrons. So we have 6 for the sulfur plus 6 for the oxygens, and there's 4 of them. Plus we have a 2- charge, so we have 2 more. So make sure that you're always keeping track of that. And so that gets us to 32 valence electrons. Okay, and so then we'll just start counting them out. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. All right, we're done. Well, it's an ion, so we'll put our brackets and our 2- charge. All right. Now let's take a look really quick at our formal charges, because of course it's never going to be that easy. So look, sulfur wants 6 and it has 1, 2, 3, 4. So it has a +2 formal charge. Oxygen has 1, 2, 3, 4, 5, 6, 7 on all of them. It should have 6. So each one has a -1 formal charge. That's a lot of formal charges. So what can we do? Well, we're going to put some double bonds here and hopefully improve our overall number of formal charges. So we can move some double bonds around. And if you can see, if we can move these lone pairs in and these lone pairs in, then what we have is all right. And so now we've moved some double bonds in. Of course, now the octet rule is being broken, and we'll get into that in just a few slides because, of course, scientists are always lying to you because I said it has to have an octet, and now we have 2, 4, 6, 8, 10, 12. So what's going on? More on that in a second. But now we have 1, 2, 3, 4, 5, 6. So we have a 0 formal charge on this oxygen and this oxygen. We have 1, 2, 3, 4, 5, 6 out of 6 on the sulfur. So we have 0 here. And then, of course, 1, 2, 3, 4, 5, 6, 7 around this and this oxygen. So this is minimizes the formal charges. We don't have the same formal charges sitting on adjacent atoms. And our formal charges are sitting, our negative formal charges are sitting on the more electronegative atom, as oxygen is smaller than sulfur is more electronegative. And so then the idea of resonance is that there's multiple ways that we could put these double bonds. And hopefully we see that there's 2 double bonds and 4 oxygens. So instead of this double bond, I could put the double bond on this oxygen and leave that one as a single bond. So with resonance structures, we draw these double arrows. So let's see what I say I was going to do. Put it down here, put it over here, one over here. So now we have 2 different structures representing the same number of formal charges, same distribution of electrons. So these are good resonance structures of each other. There are more of them. So make sure that you're not satisfied with that, or otherwise you'll be missing points tonight. But so that's, getting you started on part 1. But make sure that you're understanding that a lot of the times, some of these breaking of octets come from these formal charge rules. And of course, we'll get into why sulfur and not oxygen can break that octet rule. The other thing that we're asked to do is find the bond order, right? So there are, let's see, I'm all about colors tonight. So we have 1, 2, 3, 4, 5, 6 bonds and 1, 2, 3, 4 bonding regions. So the bond order, BO for short, is 6 bonds over 4 regions, which gives a bond order of 1.5. All right, so let's get into a little bit more of some theory, what you're going to be seeing, what you're going to need to work with tonight. So rule 1 is there's going to be 2 rules, 2 exceptions to the rule. The first one is electron deficient atoms. So boron and beryllium can form 2 and 3 bond respectively, or I think maybe I said that backwards. But what you can see is that the octet is not filled here. There's only 4 electrons around beryllium. There's only 6 electrons around boron. But what we do see is that there is a 0, 0, 0, and 0 formal charge. We see 0 formal charges on both of these structures. If we go and try to make all of them have octets, and you can see we can do that over here. We can move some electrons in to beryllium, you can have double bonds, and everything has a complete octet. The same thing with this boron. But now look at all of our additional valence, or our additional formal charges. And so these structures are not correct. And so for beryllium and boron, we're allowed to have less than an octet or electron deficient center atoms. The other exception, of course, that we've already been looking at is expanded valence shells. The important thing is that non-metals from period 3 or higher has to be period 3. Anything in period 2 can't do this. That's really important, and that allows organic chemistry to kind of exist to the fact that period 2, carbon especially, doesn't have access to that d orbital. But it can have more than 8 electrons around the center atom. So there's situations where you can have expanded valence shells with more than 4 atoms. So if you have this sulfur tetrafluoride, you can add 2 more fluorides and you can get this sulfur hexafluoride. You can get this phosphorus pentachloride over here because sulfur and phosphorus in period 3 can access that d orbital and can expand into this, this larger shape. You can still have an expanded valence shell even if you don't have 5 or 6 or more atoms around the center atom. So that's a really important one to know. You might see ClF3 and say, well, that doesn't have an expanded valence shell because there's only 3 things around chlorine. But once you do the Lewis structure, you start counting out electrons, you get here, you're still missing 2 electrons. Where do you put them? You put them on chlorine. Why? Fluorines don't have access to the d orbital. The only one that can expand its valence shell, also the one that's in the center, is chlorine. And so it can have only 3 atom groups around it, but still have an expanded valence shell. Sulfuric acid, you take a look that we can do it without any expanded valence shell on the sulfur. Sulfur in period 3 has access to the d orbital. But of course, the actual structure of sulfuric acid, which with measurements we see that we have 2 double bond lengths and 2 single bond lengths in this structure. We do not see when we measure this in the lab 4 bonds to oxygen that are the same length, which indicates that this is the actual structure of sulfuric acid. And you can see that when we expand the valence of the center atom, then we make all the formal charges 0. One more, and we just saw this, of course, just to reiterate, right? With this sulfate atom, you have all of these formal charges, but then once you expand your octet the way that we did, and of course, more resonance structures than this. So don't think that it's just these 2. But then you see that you only have, you minimize the number of formal charges. So the 2 theories that I'm going to go through, and I'm going to explain them for brevity's sake, kind of at the same time, but I really want to make it clear that VSEPR theory and valence bond theory are separate theories that are both correct. They work in parallel with each other. So I'm going to explain them in parallel with each other. We'll do each kind of structure, both the VSEPR theory, the valence bond theory for each one. But understand that we're talking about 2 theories at once. And of course, this is simply a primer. We're not digging into this too much. But the first part, valence shell electron pair repulsion, or VSEPR theory, says that electrons want to minimize the repulsion that they experience when electron groups come into contact with each other. So like a magnet, or 2 ends of the same side of a magnet will just naturally push each other apart. And I'm using hand gestures, and I realize that maybe some of the people in the recording can't see this, but they push each other apart. And the result is that they have a really specific shape. And so in your textbook, they talk about the VSEPR theory, the 5 main shapes, and that would be the electron group shapes. Electron group would be around the center atom, would be any single bond would be 1 electron group, a double bond would be 1 electron group, a triple bond would be 1 electron group, a lone pair would be 1 electron group, or a free radical, AKA a lone electron, 1 electron group. So we're not counting the number of electrons, but just the region at which electrons sit. And so, of course, they make these 5 structures, these electron structures, because they push away from each other, and this is the maximum they can push away from each other. So if there's 2 things around the center atom, they'll form this linear structure, trigonal planar with 3, tetrahedral with 4, trigonal bipyramidal with 5, and octahedral with 6. Now, we're simply just talking about electron groups. The molecular shape, we have to start looking at what atoms are attached to this structure. So the 5 main structures, and these are all made to repel the electron groups as far as possible. So in linear, you have 180-degree repulsion. The max you can get with 3 is 120. 109.5 is the angle with the tetrahedral shape. Trigonal bipyramidal is the only one that has 2. It has a 90-degree from up here from these equatorial atoms around the equator, and then you have these top and bottom. So they're 90 apart from each other, and then the 3 around the equator are 120 away from each other. And then when we have 6, there's only one thing we can do. It's like a jack, if anybody ever played jacks as a kid, which I'm guessing nobody did. But they have this shape, And all of these atoms in this structure have 90 degrees separation from one another. But again, there's two things that we always have to think about. This is so important when you're doing this test. There's always two things. One, how many electron groups are there? That's the electron group arrangement. There's only 5 options for that. These are the 5. If there's 2, it's linear. If there's 3, there's 4, 5, if it's octahedral. So you can only have these 5. The other thing though is that if there's a lone pair, then you kind of have a missing atom and it changes the shape a little bit. So there's the electron group that we have to count, and then we have to figure out what the molecular shape is. The other theory that we're going to be talking is valence bond theory, and valence bond theory says that methane doesn't form only 2 bonds with those 2 p orbitals, or possibly, we'll get into all of the different options of exciting electrons, but all of them would involve different length bonds. But that's not what we find. What we find is, because of this hybridization, that we have the same strength, the same length bonds in a centralized molecule, because the valence orbitals are hybridized to new orbitals called hybrid orbitals. And that's the main idea behind valence bond theory, is that these individual orbitals hybridize to make all the same orbitals. 3 things I want you to take away from valence bond theory. 1, the number of hybrid orbitals equals the number of atomic orbitals mixed, simply counting. An s and a p make 2 sp. S and 2 p's make 3 sp2s. We'll get into it. Number 2, so the type of hybrid orbital is going to vary with how many atomic orbitals were mixed. And I was just saying that 2 of them, an s and a p, will make an sp, or 2 of them. An s and 2 p's will make 3 sp2 hybrid orbitals, so different than the sp orbitals, different shape, different strength, different length. And then finally, the whole idea behind valence bond theory, the reason that they hybridize is so that the shape and orientation maximizes orbital overlap. We want to minimize the energetic level of the system. And so maximizing overlap best minimizes the energy of the system. And that's what valence bond theory is trying to achieve. So let's look at both the molecular, electronic, and hybridization of all of these structures. So the first and simplest is linear. There's not much that we can do here. We have a linear electron shape. So we have 2 electron groups here. We have 2 electron groups here. Single bonds, double bonds, they just count as electron groups. Now we can't have only 1 atom here, because then it's not really a shape. It's just 2 points make a line always. So the linear electron group always makes linear molecular shapes. Simple enough. And they'll always repel each other. These electron groups will always repel each other 180 degrees. So an s and a p orbital, so if you only have 2 electron groups, you only need to make 2 bonds. And so what you'll do is you'll mix one of your s orbitals, one of your p orbitals like this, to make 2 identical sp orbitals, which will look something like this, which you can see maximizes the overlap with this huge shape and is able to do better bonding, and more importantly, has the same strength, the same length, shape orbitals for both bonds, rather than having this circular orbital here and this lobing orbital here. And again, 1 s and 1 p make 2 sp orbitals. And again, this is the idea. If you have beryllium, I already said that with the reduced valency that beryllium can bond twice, doesn't have a full octet, but it can still do this. How? If it only has 2 2s orbitals, and everything that we know about how electrons fill says that there's no free electrons for bonding here. These are paired electrons. So why is a bond even formed? Well, maybe 1 s orbital is excited to the p orbital. Well, then you'd have an s bond and a p bond, and well, those would have different shapes and different lengths and different strengths. They don't. What happens is this mixing, this slightly higher energetic but lower energetic than the idea of exciting 2 electrons to the p orbitals. So better is to mix and make 2 new orbitals, which are sp orbitals. And keep in mind, and of course I'm sketching all over the place and making this unclear, that then you are mixing a p and an s orbital, and so you have 2 orbitals here that are unhybridized and left over. And so you see those here at the same energetic level that they started at. The only thing that lowers the energetic level of these orbitals is the hybridization process. Okay, a little more complicated. So now if we have 3 electron groups, we have the trigonal planar electron shape, so 120 degrees between each. But if one of those electron groups is a lone pair, then a couple things happen. One, the actual shape of the molecule is no longer trigonal planar, because the electrons, we picture them as not really visually existing. So we don't really see them. And so the shape is bent or V-shaped with one lone pair. We see that. The other thing that happens is that we go from 120 degrees between each of the different electron groups to less than that by quite a bit. So the electrons in the lone pair will push down harder than just the same electron groups would and shrink this. And so whenever we have a lone pair, we always expect that the ideal angle will decrease. So it will not be the ideal angle, and that lone pair will push those other remaining electron groups closer to each other than they would like, and thus have an angle that's always less than the ideal angle. So this is what the sp2 hybridization looks like. Again, if we have 3 electron groups, then we have 2 s orbitals and a p orbital. But we don't have only one bond here. We have 3 bonds around boron. And so we have this hybridization of 3 sp2 orbitals and this one leftover equi-energetic 2p orbital, which is unhybridized. And so there's 3 bonds that are made, and so you can see this p orbital that's left alone. Okay, so tetrahedral is the last of our 2 and above period possibilities. So this is when we're bonded with 4 electron groups, the maximum for an octet before we start expanding our octet. And so we have a few choices. So the first thing is that each electron group is connected, as in methane. I've been talking about methane all class. We would have this 4-direction shape called tetrahedral with an angle of 109.5 between each of the hydrogens. We can then put a lone pair like in ammonia. And so then, of course, a couple things are going to happen. We'll change the shape. So now we have an electron shape that's tetrahedral and a molecular shape that's tetrahedral. We get rid of a lone pair, and now we kind of have this pyramidal that's trigonal. So we call this trigonal pyramidal, very creative as scientists. And the lone pair squishes this angle to 107.3, so less than 109.5. So this shape, when you have a tetrahedral electron configuration and one lone pair, is a trigonal pyramidal shape. And then the other thing, and these shapes don't have to be original, if we put 2 lone pairs as in water here, then we come back to this bent shape. So we can get bent shapes and linear shapes and things with a lot of different electron configurations. So again, you don't want to take any shortcuts here, because you can have a tetrahedral electron configuration and a trigonal planar electron configuration. And both of those molecules could have a molecular shape of bent. So make sure that you're keeping track of that. And of course, 2 lone pairs are going to push down even further on these hydrogens and squishing this angle that was originally 109.5 to 104.5. And so you can see that as you add more lone pairs to this tetrahedral electron configuration, you increasingly, or you decrease in a systematic way, this bond angle from 109 to 104. So the more lone pairs, the more that this is decreased, this ideal angle. Okay, and so then this is just the sp3 hybridization, what I've been saying this whole time. How does this form 4 identical bonds? This methane, we have it right here, carbon, 4 hydrogens. And it does it by hybridizing 1 s and all 3 p orbitals to 4 sp3 hybridized orbitals. And so then the carbon bonds 4 identical bonds to 4 hydrogens having the same length, strength, same bond order. Hydrogen doesn't have to hybridize, so it just bonds with its 1s orbital. What does it look like when we have lone pairs? Well, it still hybridizes. It's just that a lone pair sits in that hybrid orbital. So for ammonia, we have 5 electrons here, 3 in the p orbital, 2 in the s. They hybridize to 4 sp3 orbitals, and we have a lone pair sitting in one. And then, of course, with water, we have 2 paired up orbitals and 2 orbitals with only 1 electron. And so we get 4 hybridized sp3 orbitals, but only 2 with bonding electrons and 2 with lone pairs. All right, and so let's just dig into some of the last shapes, and then I will do one example which comes straight from your work, and I'm going to give you all of the little parts. So we'll work through one example of all of these little questions, and you'll see what the lab will be like, and I can answer any questions then. So the last ones, now we are expanding our octet. So of course everybody is saying, well, of course this has to be any element from period 3 or beyond, because anything from period 2 or period 1 doesn't have access to the d orbital, Michael. And I get it, you guys are all experts, but just bear with me here a little bit longer. So the trigonal bipyramidal electron configuration is when you have 5 electron groups around your core atom from period 3 or above. This shape is because around the equator, this equatorial shape, we have a trigonal shape around here, 3 that are all 120 degrees from one another. And then we have 1 going up and 1 going down, which are 90 degrees from each other. So this is trigonal bipyramidal, as you could picture as trigonal shape, and then a pyramid on the top and a pyramid on the bottom. So that's when you have 5 bonding groups, and the ideal angles are 90 and 120. So when we add 1 lone pair, now we're going to always add the lone pairs in this configuration to these equatorial spaces. And so the lone pair will sit here. It's going to push everything away from it a little bit more. And so as a result, we're going to have less than 90 and less than 120 angles. And this is called a seesaw. I think the idea is like this, the old children's toy, you know, with the kids, you understand, a seesaw. So that's the idea of that shape, it's just kind of turned on its side. And that's what happens when we have 5 electron groups, but only 4 bonding groups, only 4 atoms bonded to it and 1 lone pair, we get the seesaw shape. Of course, continuing on, we could put 2 sets of lone pairs, again, both coming from that equatorial region, and they are going to push even more. So look, you're getting to 86.2 degrees here between these, what should be 90 degrees. There is both of these around the equator have lone pairs, and so there's no more 120 degree angles. There's only 1 along the equator, so there's just these 90 degrees or less than 90 degree shapes. We call this T-shaped. Of course, it's not a perfect T because of the suppression of those angles by the lone pairs, but we can see it kind of as a T. And then finally, and this is a really important one, I think, to take away. If I was writing a test, I might put something like this on the test, because now we've got an expanded valence. We have 5 electron groups, but what happens? We have 3 lone pairs, and they're all replaced along the equator. These accitorial atoms stay the same. And so as a result, we get back to a linear shape, and these repel both of the atoms exactly the same, and they all repel exactly the same. And as a result, we kind of go from these non-ideal angles back to ideal. So with the trigonal bipyramidal electron configuration, with 2 bonding groups, we get to a linear shape, and that has the ideal 180 degree angle. So that's an important thing to note, 180 degrees there. And of course, now I've mentioned this probably way too much, but you have to have access to this d orbital for this expanded valency. So now we're going to mix 1 s, 3 p's, and 1 d orbital to make 5 sp3d orbitals that look like this, and leaving 4 unhybridized d orbitals. They're not really shown here. In this structure, you can see that the chlorines, they don't need to hybridize, so they're using their 3p orbitals to bond, each one of them to bond with one of the 5 sp3d orbitals. And then the last group, of course, is octahedral. And if anybody is wondering, there are more groups beyond this. There is square bipyramidal, but we tend to just talk at this point to this. But there is more. If it feels like, hey, why are you just stopping here? Because this is normally what textbooks cover. This is what most normal molecules will look like. Even most non-normal molecules will look like. But you can expand the valency even further. So if you have 6 electron groups and 6 bonding electrons, then you have an octahedral shape with 90 degrees between each atom, like the Jack. If you put one lone pair on, you're going to remove it from, well, any one of them. They're all symmetrical at this point. And you're going to get this square pyramidal shape. So the idea is that there's a square here on the bottom, and then a pyramid shape like this. Terrible drawing. And of course, remember that the lone pair is going to push them all up a little bit more, which means that this bond angle is going to decrease from ideal, so less than 90. But of course, because I have to make it confusing, if you put two lone pairs on, like in this xenon tetrafluoride, then this lone pair will push down on all four of them, and this lone pair will push up on all four of them. And as a result, you go from ideal angle to not ideal angle, back to ideal. So back to 90 degrees, because both are repelling each other in the same way, in a symmetrical way. So with two lone pairs, we get to this shape, and we just call this square planar. So it's flat and square. And of course, now we need 6 orbitals. So we will need 1, 2, 3, 4, and 2 d orbitals, 5, 6, to make 6 sp3d2 orbitals. And that will leave behind 3 unhybridized 3d orbitals. And so you can see the sulfur is now bonded 6 times with 3 equi-energetic orbitals, and the F doesn't need to hybridize because it's only bonding to one thing. So it's going to go ahead and just use that 1 electron in that last 2p orbital to bond with each of the 6 sp3d2 orbitals. One more thing to cover, and then we'll do our one big example, and then we'll call it. We need to know the 2 different types of bonds. The first type of bond is a sigma bond. Any single bonds are sigma bonds. Sigma bonds have all the electron density in between the axis, the bonding axis. And so as a result, rotation is free around sigma bonds. The other kind of bonds, when the p orbitals are close enough, like in carbon, to overlap, you can have a sigma bond. And if there are electrons in these unhybridized p orbitals, they can overlap on the top and the bottom to make a pi bond. So there's these lobes of electron density. One pi bond has 2 lobes, above and below. So that's a single double bond. There's a sigma bond and a pi bond, which has 2 lobes. And again, you can see the electron density sits above and below. And as a result, it stops the rotation around the bond. So any double or triple bonds cannot rotate because of these lobes of electron density, but any single bonds are free to rotate around the bond axis. So that's an important thing to identify. So every double bond has a sigma bond in it and a pi bond. A triple bond has a sigma bond in it and 2 pi bonds. And a single bond has no pi bonds and a sigma bond. So we'll have to make sure that we're ready to count all of those up, but let's practice. Okay, so this is the kind of thing that we'll be looking at tonight. So we have sulfur tetraboride, and we want to draw the Lewis structure. We want to count electron domains, bonding domains, lone pairs on the central atom, hybridization of the central atom, electron geometry, molecular geometry, BR/SBR bond angles, number of sigma bonds, number of pi bonds, types of bonding orbitals in the bromine, and we want to know if it's polar. If you can do all of this, you're in good shape. So let's get into it really quick and see how easy this can be. So first we'll start with the Lewis structure. We'll build our skeletal structure with our sulfur, which is of course in group, I've done this enough already, 16, where bromine is in group 17. Put the bromine around. Such, we'll count up our valence electrons. So 6 plus 7 times 4. That gets us to 34 valence electrons. So we'll start putting our bonds in: 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Sulfur is in period 3. We can expand its octet, 34. So how many electron domains do we have? So we have 1, 2, the lone pair, 3, 4, 5 electron domains. And so How many bonding domains? Well, one lone pair, that's non-bonding. So there's 1, 2, 3, 4 bonding domains. How many lone pairs on the central atom? 1. Again, if you didn't do the train is going by so loud. If you didn't do the Lewis structure correctly, there's no way that you could answer these questions successfully. Hybridization on the central atom, well, there's 5 electron domains, which means that we're going to need to have 5 orbitals to hybridize. So an S, 3 P's, and a D. So we'll have sp3d. There's going to be 5 of them. And so we'll start by filling 1 electron in each orbital. And then there's a 6th. So there's the 4 bonding orbitals and the 1 lone pair in the 5 sp3d orbitals. So the electron geometry then with 5 electron domains is going to be trigonal, bipyramidal. Oops. That's supposed to be bipyramidal. Sorry about that. Handwriting. Okay, and then if we have 1 lone pair, and this is where that practice comes in. So we have 1 lone pair, so we have this seesaw shape, which are our children over here. Oops. So we know that with 1 lone pair and the 3 left over, that we'll have a seesaw shape. All right, and then the next question is about bond angles. So if we think about what this molecule actually looks like, to draw it a little bit nicer. So if we have our sulfur, we have our equatorial bromines. I'll leave out the lone pairs for now. So we have this bond angle, this equatorial bond angle here, and then we have this axial bond angle here. We know that they're going to be less than, because that lone pair is going to push those extra, those bonding groups a little bit further than we would expect. And so we should have less than 90 degrees with this bond up here, and less than 120 degrees for this bond right here. So number of sigma bonds. So we have 1, 2, 3, 4 sigma bonds. How many pi bonds do we have? Well, none. There's no double bonds. There's no triple bonds. So no pi bonds in this example. My pen. There we go. 0. Okay, and then lastly, oh wait, no, 2 more. Type of bonding, orbital, and bromine. Well, bromine doesn't have to hybridize. It's only making 1 bond. There's no need to make some new equa-energetic bonds. And so bromine is just going to use its free electron. It's got that 1 p electron in its, bromine has 1 p electron in its 4p orbital. So it's going to bond simply with its 4p orbital electron. The center atom sulfur will have this hybridized orbitals. And so then finally the question is it polar? Well, so I'll just tell you that the electronegativity, the sulfur electronegativity is 2.5 dBi, and the bromine electronegativity is 2.8. You'll want to have these looked up. So that means that the, running out of space here, the delta En, right, the change in electronegativity between them is about 0.3. It's not very polar, but it's still a polar bond. And especially the thing that we want to consider is not just the polarity of the bond, but the shape of the molecule. If the molecule cancels in every direction, if each has the same dipole, but say this lone pair wasn't here and there's 5 bromines, then all of those dipoles would cancel and it would be a nonpolar molecule, even with a polar bond. But because it's a seesaw shape, we have these dipoles. They're all going from the sulfur, to the bromine. And the overall structure of this vector will have some vector, let's see, I guess it's going to look like this overall in the molecule, making it, in fact, yes, a polar molecule. And that's it. Those are the things that you want to be able to know before the test, before the final. You want to be able to take a molecule like this, beyond naming it, nomenclature from like the first few weeks. You want to be able to move through this checklist. If you feel like you can move through this checklist, no problem, then this lab will be very doable for you. If there is one aspect of this part that you don't understand, then that, like say hybridization, which is something that people struggle with, then that's what you want to go and get help with as soon as possible from your instructors. All right, well, it's time to shape up and ship out. That's my little molecular shape question, joke. So are there any questions?